A week ago I got this comment on a previous video, nerds96. So I bought one of those units, TinyPFA. I have started to investigate it. Here are 4 measurements where I run one channel with my Wenzel oscillator and the other channel is a rubidium controlled oscillator. 2 traces are with the rubidium as the reference, while the test object is the Wenzel, and 2 traces are the other way around, the Wenzel as the reference and the rubidium as the test oscillator. All the curves seem to fall within a common error limit, because the uncertainty at the right-hand side is fairly large, and somewhere in between all of them is within the error limits of all the measurements, almost at least. And at short times the agreement is very good. When I remove all traces except one, you can see the error limits, how large they are out here. So actually above 100 seconds these curves are not very interesting to compare. I have connected a GPS disciplined oscillator. I know it has much lower sideband noise at 1 Hz offset from the carrier. And here I can see I have 2 traces. They differ more than expected. I don't know why. And here is what I had before, when there was the rubidium controlled oscillator. In both cases measured against the Wenzel oscillator as a reference. I have placed the Wenzel oscillator inside a box in another room, and I feed it from a power supply next door, and I have big capacitors connected here close to the Wenzel. These are 0.1 farad. They are series connected 2 and 2, so together 150,000 microfarads. And these are 3 times 39,000. So it's a bit more than 350,000 microfarads here. I am running Linrad and TimeLab at the same time. The test object is the GPS disciplined oscillator, and Linrad has its own set of 2 10 MHz oscillators. One, channel 2, is not so good as channel 1. Channel 2 is the red trace, channel 1 is the green. The yellow trace is the correlation between these 2 measurements. Running for 5 hours and 50 minutes. The Allan deviation of TimeLab is with the Wenzel oscillator in the box as the reference. It is now lower than it was before. If I look at 10 seconds, I see here 4 times 10 to minus 12. And in Linrad, if I look at 10 seconds, I have to click on it first. 10 seconds. It says 2 times 10 to minus 12. So it differs by a factor 2. If I look at 1 second, it says 1.6, and TimeLab says 1.3 times 10 to minus 11, and Linrad 1.6 times 10 to minus 12. So there is a very big difference. And as you see, Linrad is flat from 1 second down to 0.02 seconds, while TimeLab steeps upwards very rapidly. I can load the old measurements, and it's obvious that the big noise here was due to the Wenzel. And why the noise is much higher here at 1 second, I don't know yet, but I have some suspicions. Here is frequency versus time for the latest measurement with the vent cell in the box in the other room. And this is 5 hours, and one division. It's hard to see how much it is, but I can select a time here and see the frequency is in the last decimals 7.22 Hertz. And if I switch to a point where there is one division lower, it's about here. It says 7.22 Hertz also. So I go from here, that is 7.2223, and here is 7.220. So it is 3 millihertz. It seems it is 1 millihertz per division here. Here is the frequency versus time for the two old measurements. And we can see there were some events towards the end of the measurements, and they were responsible probably for that extra peak in the Allan deviation. When I zoom in time, so I here look only at the first, at about 10 seconds, I see a very strong oscillation at this particular point in time. And that is the explanation why the Allan deviation has this structure here. The selected trace, if I remove that, we can see this structure. I can then look at the modified Allan deviation, which should filter out things close to the carrier, and then it becomes much better. There is some kind of problem here. The region with very strong oscillations is from here to here, about 400 seconds or so. Then that width of the trace is smaller. I can pick some region in time, like here. And here the amplitude is what you can see here. I cannot easily zoom to another point getting the same scale. I don't know how it works, but I zoom into it and it looks like this. And I can look at the other trace. Here is a different situation where the phase doesn't change except up and down occasionally. If I zoom out, you can see how the behavior is. So there is a quantization problem of some kind here. When I look at the latest measurement from 6,000 seconds and onwards, the width of the shaded area is very large. When I zoom in somewhere where the shaded area is large, I find this structure for the frequency, and the frequency at the flat place here is 7.220 as the last numbers, but on the peak it says 7.230. That's 10 millihertz. That's a very high jump in the frequency. Here I have started a new measurement, the red trace. I will disable the old ones. And now I have a very strong modulation, and that will be visible in the frequency measurement. It looks like this when I look at a much shorter time, and I select another even shorter period of time to look at, and it looks like this. So something is wrong. I have to reset the TinyPFA. I have switched off and then switched on the TinyPFA, and also after that set the PLL to lock on the channel A, while channel B was not connected to anything. And now I start measurement again. And this looks much better. If I look at the Allan deviation, it looks like this. And the level is very low. If I look at the function I saved during the night, it was this curve. So it is much lower at short times. So this is the proper result. So here is the frequency versus time for the ongoing measurement, and you see the numbers are 10 to minus 11 here, so it's a very expanded scale. What happens here is that I change the supply voltage by 10 millivolts. And then the frequency makes a big jump in this scale. And that's rather interesting. That tells me why I had some problems with the previous power supply. Here we can see the quantization problem. At some times we have this situation and sometimes this situation. I can magnify it a bit. I clear Linrad, that is Alt-Z, and at the same time start the measurement with the time lab. And time lab now has the floor at 2 times 10 to minus 12 at half a second, and Linrad has 1.5 times 10 to minus 12. So they agree reasonably well. And I don't understand what's going on really. I know that this up and down is caused by the quantization noise, so it is reasonable to use modified Allan deviation to remove that. And then it looks like this. And it goes down to 10 to minus 12 from 0.3 Hertz. I can try to sample more frequently. I have set tau to 0.02 seconds, so I get more points and a better result at 5 seconds, and much more of this quantization noise between 0.1 and 1 second. So I check again the modified Allan, and it looks like this. Now I start measurement of frequencies rather than phase differences. And this looks more like it to me. Well, I stop here and start again to look at reproducibility, and it looks perfect. And then at longer times, maybe it differs a little. But very little. No, a little more here. But we can see the error bars. I will wait for a while. I clear the traces in Linrad, Alt-Z, and then I go to the time lab and start a new measurement at the same time. So I know they have been using the same information. Now 9 hours and 8 minutes have elapsed, and I have results both from Linrad and from the TinyPFA with the time lab. And results are reasonably in agreement. In Linrad, the Allan deviation is flat from 0.1 second up to about 20 seconds. Then it curves upwards, and that is because the correlation, the yellow trace, works up to nearly 20 seconds, but at longer times there is correlation between the two channels because there is the PLL loop and some of the noise on channel 1 is transferred to channel 2. And at 200 seconds they are completely phase locked, so the channel 2, the noisy channel 2, is not more noisy than channel 1 because they are locked. So what we see here is the noise from my channel 1 local oscillator. And here is the result of the measurement, the noise from the GPS oscillator. And what we see here is not really Allan deviation. It is modified Allan deviation because here is a filter that removes everything that is outside plus minus maybe 22 hertz or so. So if I would open that filter, and if I could be without this spur, there would be a little bit more noise. And then maybe it would be in agreement with the Allan deviation. I can change to modified Allan deviation, and then there is a filter that is applied that brings down the noise at this range. At 10 seconds it is now 1.66, and in Linrad 1.62 times 10 to minus 12 in both cases. And 10 seconds, I should have clicked at 10 seconds, it is 1.75, which is in agreement. There is a problem with the TinyPFA at very short times. This slope upwards here, that is an artifact of the measurement system, I think. Anyway, 30 seconds, Linrad is no longer correct, probably because these two traces are correlated. But I read 3.6, and 30 seconds here, I read 1.82. So that is a limitation of my system. I need a better oscillator for channel 2, then I could read up to maybe 30 seconds or so. Here is the latest time, frequency versus time. Channel 1 green and channel 2 red, and we can see the difference. Here is frequency versus time in time lab. Something happened at the end of the measurement. I will magnify it. This does not look right. Suddenly, at this time, it seems that the system doesn't work properly anymore. If I try to magnify this flat region, I see it is just a single value, all the time the same. I can save the data, giving it some funny name, XXX, and save. And then I open the file in a text editor. And it looks like this, and here we have the initial values. And when I look at the end of the file, we can see it is the values actually are different. Very odd. I can load the file into TimeLab. Have a look at what happens now. Here you can see the development over time, how this is gradually increasing. And then have a look here, how this comes up suddenly. And this is growing all the time. And then there was an event towards the end of the file. The measurement of Allan deviation is really complicated. I don't know what caused this, if it was something with the GPS receiver or some interference somewhere. But it is at several hundred seconds and hard to see. I have connected the better of the two rubidium-controlled oscillators, and I reset Linrad and start TimeLab to see where it comes. And it is more noisy than the GPS. That is known since before. But I will leave it for quite some time to see what happens at several hundred seconds, where it should be probably better. 6.5 hours have elapsed, and of course Linrad says the same thing, 6 hours 32 minutes. When I look at 10 seconds, I see here, well, Allan deviation at 10 seconds is 3.04 times 10 to minus 12. And if I look at 10 seconds in Linrad, it says 3.86 times 10 to minus 12. And we can see in the baseband here the very strong noise from the rubidium oscillator. It was entirely black when I used the GPS-controlled oscillator. And we can see the noise is about 100 times stronger, not quite, 50 times stronger at 0.1 Hertz as compared to the GPS disciplined oscillator. But when I look at 0.1 seconds with the TinyPFA, the difference is very small. So this is the noise of the PFA, and I think it's related to quantization noise somehow. And here is the noise of the rubidium-controlled oscillator all the way down here. Then probably what goes up here is the noise of the Wenzel oscillator, because that is the reference. And in Linrad, I have not waited long enough to see the full correlation picture. Now 10 hours have elapsed, and the repeated measurement on the rubidium oscillator gives a very similar result, except at the maximum time, but there the error limits are very large. The new measurement on the rubidium oscillator gives very similar results. From about here to about here, This slope is the noise of the rubidium oscillator, and I should expect to see something similar in Linrad. So I check 0.1 second, it gives 4.6 or 4.9 times 10 to minus 11. And 0.1 second in Linrad, I click on that and read 5.6 times 10 to minus 11. That's reasonably close. At 1 second I see 1.25 times 10 to minus 11. And in TimeLab I see 1.1 or 1.0 10 to minus 11. 10 seconds, no, here is 10 seconds, 3.0 or 3.5. And 10 seconds in Linrad gives 3.68. And then Linrad starts to curve here. Something else is contributing noise. Maybe I haven't waited long enough. This is only 10 hours. 20 seconds gives 3.2, and 20 seconds here gives 2.6 or 2.3. And then results diverge significantly. So from this study I can conclude something about the noise floor of the TimeLab unit itself. And that is this red curve that I got with the GPS receiver, which is very much more quiet in the spectrum from 1 hertz up to 10 hertz or so. When I look at frequency versus time, I see something very odd. There is a jump here on both measurements, and that cannot possibly be a real phenomenon. When I magnify it, this is what I see. At the same time, here, 9 hours, 6 minutes and 10 seconds about, there is a jump in the frequency. And the particular thing is that in the first measurement, the jump was to an unrealistic value. It doesn't change at all. In the new measurement, there was a jump a little softer. I can look in more detail. And here it is not so clearly visible, but you can see. And then it goes up. And it is at this point. 3,000 to 32,768 samples. Sounds familiar somehow. Well, 32,768 seconds. This is a power of 2. So what we see here is a software problem in TimeLab. I have to remove some samples to see what happens when we don't include this step. But first I check for updates. Check now. And there is a newer version from 5th of June. It is very recent. Today is 9th of June. So now I am running the very latest version, and the problem is still there. I have saved the measurements. I will load and look at the curves as they grow while the file is read into memory. So we look at what happens here towards the end of the measurement. This looks nice, but now there was some event. So I think that is a software bug. I have edited the TIM file, and I can magnify this interesting section here, and then I can remove the visibility of the edited file. You can see it exactly the same, but at the point where it starts to go up, I have removed the data. Then when I look at the Allan deviation, you can see there is a significant difference. The blue trace is the edited file, and it looks much more nice without this structure here. So I will also edit the other file and compare the edited files. First, I compare the edited file with the earlier measurement of the rubidium oscillator, which was only 6 hours. And now I find they are very close to each other in this range where the rubidium oscillator is determining the Allan deviation. At longer times, the Wenzel oscillator is also involved, and it may vary a little bit. Here is the same thing for the measurement on the GPS stabilized oscillator. Here is the original measurement with a jump to a constant frequency at 32,768 seconds. I have edited, and the new file is here. And we don't see it because I have to remove this original file first, and then I can show here. So I have just removed that jump. It has a consequence for the measurement on the Allan deviation. There is a big difference here. This structure was caused by that jump at 32,768. I want to know whether it matters if one sends phases or frequencies from the TinyPFA to TimeLab. And as it turns out, it doesn't matter. I have made 3 measurements of 5 minutes each, one sending unwrapped phases and the other sending frequencies. And the traces, which are different versions of red, they are frequencies, and different versions of blue, they are phases. And I don't think there is any significant difference. If I look at modified Allan deviation, it doesn't make much difference. And I can look at Hadamard, and it looks like this. Statistically, one could say that the blue traces, one is between the 3 red ones, but 2 are a little bit below. This could be meaningful, or maybe it is not. Although at tau 0.3 seconds here, there is a significant difference. The blue traces are all very close to each other, and the red traces are a little bit below. And the same for 0.4 seconds. 1.4 for the red ones times 10 to minus 12, and 1.7 for the blue traces. That's for phases. When I look at the TIM file for unwrapped phases, I see there are 10 valid digits from here to here. Then comes 7, 7 and zeros, or 7, 7 and almost 0, 699. And this is the same all the way through the file. The TIM file for frequencies is different. This looks very odd. The first digit steps up,
and then it steps much slower. And then there is a row of zeros, and then seems to be valid digits. And when I step down through this file, some rather long distance, it starts to look normal. Seems to be a software problem to me. Something like here. This is line number 1100. That starts to look normal. But when I look further down the frequency file, I find these two are always 0, 0, 0. And this cannot be valid frequency information. Maybe it is coded some odd way, or maybe it's just by chance that the first 3 digits gives good enough information for the noise. I don't know. The frequency data, when I have the time lab in monitor mode, it shows 12.780 and then something around 5. But there are 6 digits and they look perfectly normal. So there must be some conversion before it becomes a TIM file. I guess it goes over to phases again.
The TinyPFA also says 12.780 and it shows 5 digits after that.
When I send unwrapped phases, what I see is consistent with what I see in the TIM file. There are some valid numbers up to here, and then it says 777. And in the TIM file there are decimals after the 7s, and they don't mean anything. And there are so many valid digits here, so this looks okay and good. And the funny thing, I don't see any difference on the graphs that are presented. Here are 2 plots of Allan deviation with a GPS disciplined oscillator and the Wenzel oscillator as the reference. The spectrum, the sideband noise of this oscillator looks like this. It goes from about 100 at 1 Hertz, minus 102 dBc per Hertz at 1 Hertz, and about 160, minus 160 at 1 kilohertz. I have degraded the flat noise floor by adding a big attenuator followed by several amplifiers. This is what it looked like before, from minus 162 up to 102. And now it is unchanged below about 3 Hertz. And then it stays at minus 114 about. This is what happens in the Allan deviation curve. The 2 red traces are with the noise added. I can now change to look at modified Allan deviation. It is said that one can see the difference between the flat noise floor and noise that decreases when the distance from the carrier is increased. Well, there is not much conclusion I can draw from this. I have connected the rubidium stabilized oscillator. It is really noisy close to the carrier. I have to change the 0 point of the scale to be able to see. It starts at 76, while the old started at 102, minus in both cases. So that is 30 decibels more noisy at 1 Hertz. And this is very visible in the Allan deviation. Now we can see the difference between Allan deviation and modified Allan deviation. So, green trace, that is with noise close to the carrier. Red trace is with a flat noise floor that is very strong. And the red trace goes down much more than the green. So modified and normal. And here the red, normal Allan and modified Allan. And here there is a factor of 10. And now there is a factor of maybe 5. To see this better, I would need an even more degraded GPS receiver. We'll see if we can add one more amplifier without getting oscillations. The signal from the GPS disciplined oscillator is now attenuated by 90 decibels, then amplified and split to send -5 dBm into the Linrad system as well as into the TinyPFA. The flat noise floor is at -92.5 dBc per Hertz, from 2 Hertz up to some very high offset, and at 1 Hertz it is -91. When I look at the Allan deviation, then we see very clearly it's the brown trace here which is the flat noise floor, while the green trace was the rubidium oscillator with a lot of noise close to the carrier. If I now go for modified Allan deviation, here we can see that the brown trace goes down all the way to 10 to -12 here. I can set a mark there. And I go back to Allan deviation. And then it is much higher. So here is what people talk about. One can see the difference. Well, it is far better seen in the frequency domain. And here is the limitation of the measurement system. And that is also improved a lot if I go for the modified Allan. In Linrad, I have another kind of filter before the Allan evaluation. It is the baseband filter. If it is wide open like this and with a very strong flat noise floor, I get this curve that steeps with a theoretical a factor of 10 for a factor of 10 in frequency. I can reduce the bandwidth like this, for example, with much narrower filter and then clear. And you can see how this curve is much lower. And since the bandwidth doesn't allow more than about, what can it be, 5 Hertz, I should expect the noise to disappear at shorter times than 1/5 Hertz. So I have the slope here, the normal linear that I had before, and not for a very long distance, because the limitations of my system will come into play. It will take some time to get statistics here.